So this is the last section in Chapter 1, and so in this we're going to talk about the distinctions between different mixtures and matter. If this thing decides to go. There we go. Alright, so first up you really have two different types of mixtures. They can be split into more specific types, but for the most part you just have homogeneous and heterogeneous mixtures. So homogeneous, homo basically meaning the same. So a homogeneous mixture is a mixture with uniform composition. It's also known as a solution. Okay, so you're more familiar with these than you might think. It's just most people don't go around calling their drinks homogeneous mixtures. Try that at lunch tomorrow and see what happens. But then you also have heterogeneous mixtures. So these are mixtures that do not have uniform composition. Yet again, this is something that you're probably a little bit more familiar with, but generally you don't call, like, say, your salad a heterogeneous mixture. Okay, so we're going to go through a couple different examples of these, but the properties of a mixture depend on really what's mixed in the mixture and then also in what concentrations, what amounts that are mixed. So you have also a pure substance. So a pure substance is something that is just that substance. Okay, it has a fixed composition, and you're not gonna, like, if you zoomed in on something. Sorry, my dog's barking. Give me a second. Sorry, my dog is really big on that whole stranger danger thing, and he does it with everybody, no matter if he knows them or not. But anyway, so pure substance has a very fixed composition. It doesn't necessarily mean that it's a pure element, so it's just one element. It's talking about a substance. So if you have pure water, that's pure H2O. So two hydrogens, one oxygen, but they're all bonded together in the same way. So they're a fixed composition. So every sample of a given pure substance will have the exact same characteristic properties. Okay? And you can usually use those properties to identify the substance. Oftentimes you'll have to look at several properties just to kind of narrow down what substance it is that you're looking at. But, you know. Okay. So for an example, every sample of a pure substance has the exact same composition. So like I said earlier, pure water is made out of 11.2% hydrogen and 88.8% oxygen by mass. Pure substances can be either compounds or elements, so you can have pure carbon. Okay, that actually comes in several different forms, such as diamond, graphite, carbon nanotubes, things like that, or it can be a substance. So this is looking closer at the mixtures. So with a homogeneous mixture, you're not going to be able to see any particulates kind of settling out like you do in this heterogeneous mixture here. Okay, so it means that anything that is dissolved in the water of this solution is perfectly suspended in the water. Okay, so you don't have like layers in the mixture. You're not going to have, say, the sugar models in this sugar molecules in this example falling to the bottom of the solution and basically dropping out of the solution. Okay, so no matter where you zoom in on this solution, okay, just to look at the molecular level, you're always going to see sugar and water molecules. Now if we move over to the heterogeneous mixture, okay, this is where you are going to see some of that separation between the molecules, some layering. Okay, and this generally, well, usually this has to do with the bonds inside the different molecules, how the molecules interact, like the interactions between the water and the, in this case, silicon dioxide, just sand. So silicon dioxide doesn't necessarily like water. It doesn't dissolve in water, so it will not form a homogeneous mixture. Heterogeneous mixtures are relatively easy to spot because if you mix them up, oftentimes you will have something falling out of the solution. So you can see that with the sand here. So classifying matter, okay, you either have a pure substance, which is just one kind of atom or molecule, or you have a mixture that has more than one type of atom or molecule. So if you're looking at pure substance, you can split that either into an element, so it's just a single kind of atom. Okay, so one element, whether it's one or more atoms, doesn't really matter as long as both of those atoms are the same type of element. Or you can have compounds, so you're looking at different elements bonded together. And then when you move over to mixtures, again, you can have a uniform composition, a homogeneous mixture, or you can have a non-uniform kind of helter-skelter kind of mixture called a heterogeneous mixture. Another way to kind of help you think through that, all right, so this is looking at basically even with mixtures, even if it is a homogeneous mixture, you can actually separate the different components, the different compounds. Okay, oftentimes you'll have to go to kind of extreme measures in some cases. Like in order to separate sugar and water, you would actually have to evaporate the water, either using heat or just leave it somewhere for a while. But that would separate the water molecules from the sugar, and that's actually how they make rock candy. So this is looking at matter. Can it be separated? If it can't be separated, okay, so you only, you can't separate out two different compounds, then you have a pure substance. If you can separate it, you're going to have a mixture. And then, again, the question is the composition uniform? If it is, you have a homogeneous mixture. So a couple examples here: air, sugar, and water, and stainless steel. And then if you do not have a uniform composition, you have a heterogeneous mixture. Things like granite, wood, blood. The example I said earlier of salad is kind of you can picture it a little bit more example. Orange juice is another really good example. Italian dressing, okay, because all of those little particles will filter or basically settle out of the solution. Or of the mixture, rather. Okay, and then going back over to the pure substances, can it be decomposed by ordinary chemical means? If it's a no, that is an element. Okay, so you only have the one element. And then if it's a yes, you have a compound. Okay, so water, sodium chloride, sucrose, all of those have multiple types of elements involved. Alright, so some more examples here. Homogeneous, we have iced tea. Okay, maybe not the ice itself, but the tea. It's a uniform distribution of components. The components cannot be filtered out and will not settle out upon standing. That is, of course, assuming that you've made your tea properly. This isn't necessarily talking about, hot tea, you use a tea bag or anything. This is like if you're making iced tea in a tea maker. Thing. Stainless steel, again, you have a uniform distribution of components, or else you're going to have some weaknesses and kind of weird flexing inside the steel, which is not ideal for any kind of building purpose. And then maple syrup. So with maple syrup, you have the sucrose, the sugar dissolved. You have a bunch of different things dissolved in the water that makes it syrup. Makes it very viscous, so it's not really runny, so on and so forth. Then when you get into heterogeneous mixtures, you have orange juice or tomato juice. So anything that you drink that says shake well before drinking or whatever, that is a heterogeneous mixture. That is a really good indication that it's heterogeneous. Simply because in order to use it, you want it to be mixed. Okay, so if you don't mix up your orange juice every time you pour a glass, eventually you're going to get down to the bottom of it, and almost all of the pulp from the entire carton is going to be in that last cup. It's going to be nasty. Another example is a chocolate chip pecan cookie, or really any kind of chocolate chip cookie, because you have you don't have a uniform distribution or equal distribution of the chocolate chips throughout the cookie dough. Granite, again, you can look at it and you can actually see the different colors where they are. And then salad. Okay, that one is actually easy to separate by physical means. Heterogeneous mixtures are not always easy to separate by physical means, but they tend to be easier to do that than homogeneous mixtures. Alright, so talking about laboratory chemicals, when you're using laboratory chemicals, they generally have to have a very high purity. So, you know, there's a lot of warnings that come onto this, or that are printed on the bottles. There's a lot of like safety warnings, all that kind of stuff. And then there's also storage recommendations. Oftentimes you will see chemicals stored in these brown bottles. So those brown bottles are actually designed to reduce exposure to UV light, which some compounds are very light sensitive. And so if they are in light for any long period of time, they actually begin to break down. So in order to kind of preserve that purity, they will actually keep them in these brown bottles. So, interesting little factoid there. There are some grades of chemical purity. Okay, so the purest that you have is the primary standard reagents. Those are basically what everything else is tested against. So they really need to be as pure as possible. And then you get down to technical industrial chemicals. And those generally just need to have something within a range, so they don't have to be as pure. And nice thing about that is that the purer your chemicals are, the more expensive they are. So it's a lot easier to use the technical chemicals that don't have as much purity if you don't need something like super precise. Okay, so alright, and then this is going back into kind of the homogeneous mixtures. This is looking at water. Said that you could separate, or actually no, this is a pure substance, looking at water. I said earlier that you could actually separate even a pure substance by some kind of chemical means. This is an example of that. It's called electrolysis. So basically they, well, scientists will run an electric current through the water, and it's kind of fiddled with a little bit enough that they actually will break down the water molecules into their component elements. So you get hydrogen and oxygen gas from this. So this is an example of the chemical means to separate a pure substance, okay, a pure compound, into its pure elements, okay, or a mixture of the elements. But okay, so important thing to remember about that, even though you still have the same number of hydrogen and oxygen molecules, you are going to have very different properties if you're dealing with just the two gases than if you were dealing with the water. Because water is not explosive, but hydrogen and oxygen gases both are. So that could become something of a little issue. Okay, so when you're doing chemical reactions, it is always important to know like what you're going to be producing in that reaction, because you wouldn't want to do this kind of reaction right next to an open flame, because if your oxygen gas that you're producing is going right next to that flame, you're going to get a nice little fireball there, which you know, you might not want close to your face, or you shouldn't want close to your face. Anyway, alright, so that's it for this video. I've got, I think, one more slide that I'm going to have to fit into a second video.